All right. Good afternoon, everyone. It's a pleasure to have Matt Kafker give today's second talk on statistical mechanics, hard spheres, and the Wolfram model. Matt is currently a senior PhD student in theoretical nuclear physics at the University of Washington in Seattle. Before that, Matt has studied various things related to many body systems, statistical mechanics, and computational physics, which are topics very close to his heart. He has been involved in the Wolfram Physics project right from the beginning, actually, right from the first year where the physics project was introduced to the world. Matt was working on it, in fact, on these hard sphere gases, which you will see in the presentation, and he has made great progress on that. In fact, for some of you who may be interested in more practical applications of WPE ideas as well as technologies, the work that Matt has the some really amazing work that Matt has been doing over the years actually connects some of the WPP theory concepts machinery to an interesting statistical physics model. So you'll get to have a glimpse of that. Of course, Matt will also perhaps tell you a little bit about his day job in theoretical nuclear physics. You're welcome to check out his research profile. He's published some excellent papers with great collaborators. And it's really lovely to hear what he has, new interesting things that he has discovered recently in this subject. So all of you with a bent towards condensed matter or many body systems are very assuredly going to enjoy this talk. Thank you, Matt, for coming here, and go ahead.
Okay, well, thank you, Xerxes, for the nice introduction. So unfortunately, we're going to start by me trying to figure out how to get PowerPoint working. So just give me 1 second. I want to make sure that's sharing properly. What are people seeing?
It's
Are
fine. We,
people
we
seeing?
see your screen. It's fine.
Okay, statistical mechanics and kinetic theory, et cetera, et
Yes,
cetera.
yes. Yeah.
Okay, so that's that attended to. A couple more things. So my slides are in front of me here. I see your Zoom icons over here, so I'm probably going to be looking in this direction a little bit as we go through this together. I will say, whoops, this is kind of annoying. Okay, that's better. You can still see the slides?
Yes.
Okay. I will say, Xerxes, we have 2 hours, right?
Yes.
Okay, so I can talk to the void for 2 hours, but it would really be a lot nicer if you guys had your webcams on, if that's a thing you can do. Because this can be a two-way thing, or I can just sort of wear my voice out speaking to a bunch of black squares on Zoom. So for those of you who can do that, that would be great. Let's see if there's any other. Oh yes, one more thing. I'm currently recovering from a cold. So I hope to not make that your business, but you might be able to tell. I apologize about that, but these are the constraints we're working under right now. Okay, so with that out of the way, let me move this Zoom bar. Okay, let's get going. Okay, so this talk is going to be about statistical mechanics and kinetic theory in the Wolfram Physics Project. My name is Matt. My collaborators on this project are Xerxes, who introduced me, and Christopher Wolfram. I'm not sure if any of you have interacted with him at this school. And if I'll send out these slides at the end of the day here. So if people have anything they want to talk to me about, you have my email address there. Whoops. Okay. It would be good if I could change slides. Okay. So I'm a fifth-year PhD student. I work in theoretical nuclear physics at the University of Washington. I've been a member of the Wolfram Physics Project since 2020. I started at the summer school during COVID, and I've been working more or less continuously on this project since then. I've been using Wolfram language since 2018. I use member in air quotes because our title with respect to the with respect to the project changes a lot. So I've been working on these problems. I think I'm a member, but I don't know what my official title is. I'm going to spend a little bit of time talking about nuclear physics. And in fact, given that this is officially unrelated to the official topic of the talk, I've proposed a couple of problems that people might be able to work on within the Wolfram Physics Project related to nuclear physics. So I'll try to make it worth your while. I also think it'll be interesting. Primarily, we're going to be talking about classical statistical mechanics and non-equilibrium statistical mechanics. And I should say at the beginning, I'm not an expert on Wolfram physics generally, so hypergraphs and things like this, you should consider me a somewhat educated layman. I've read Stephen's work on this, but don't take my statements on these things as being those coming from a deep expert in the field, because I'm not, and you should talk to Xerxes and other people like him. And this is one of my dogs. Okay, so I'm going to start by talking about nuclear physics. Xerxes, what is my time limit on nuclear physics?
I would say 15 minutes.
15 minutes. Okay, we'll do that. There might be a little bit of wiggle room on the tail end, but if it's fun, we'll do that. Otherwise, 15 minutes. Okay, so we're going to start with the painfully obvious and then probably quickly move into things that people have seen less about. So this is sort of a standard diagram of the reductionist picture. Basically, all the matter we see on Earth is composed of atoms. This is the atomic hypothesis. People have been thinking about this in a serious way for something like 150 years. Since that time, we've learned that atoms have a lot of stuff going on. You can look at the electronic structure. You can also look at the nuclear structure and also at the subnuclear structure. And there's all sorts of things going on. We've got at least 6 orders of magnitude of length scales where interesting things are taking place. And this is probably not, it's probably more than 6. I just don't know a lot about. Once the length scales start getting really small, we start leaving my area of expertise. So atomic and molecular physics, as well as chemistry, people are thinking about electrons. High energy nuclear physics down here, people are thinking about the internal structure of protons and neutrons. This diagram was made by a high energy nuclear physicist. So you can see that they believe that the most interesting things are going on at this level, because this is the most interesting little picture. I work on low energy nuclear physics, which is what's going on in this red box here, which in this diagram looks boring, but there's a lot of good stuff to discuss. So that's what I'm going to talk about a little bit here. Concerned with the structure and dynamics of nuclei, including nuclear reactions. Oh, and by the way, this will be much more fun if it's a conversation. So at any and all times, if you have questions, chime in, because you'll get as much out of this as you put in, and that can be nothing if you don't participate. So yeah, please ask questions at any time. You can use the chat or speak up. Okay, so I'm just going to keep plowing through until somebody interrupts me. So this over here is the nuclear chart. This is basically the periodic table of elements for atomic nuclei. My claim, which is a joke, is that this is more interesting because we have 2 kinds of fermions instead of 1, which the chemists have. So what we're looking at here is each one of these little squares in this diagram is a specific nucleus. It's characterized by its number of protons, which is on the vertical axis, I believe, and the number of neutrons, which is on the horizontal axis. So if you give a proton number and a neutron number, that defines a nucleus. Each nucleus is colored according to its form of radioactive decay. So we have beta decay, positron emission, alpha decay, fission, and so on. So there's all sorts of things that are interesting about nuclei in addition to how they decay. You can look at binding energy, the size of the nucleus, the structure, excited states, dynamics, etc. Hopefully what you can see from this diagram is that nature is complex. There are some overall trends that you can see from this, from the diagram here, but it's not as if you just provide some simple mathematical function of n and z and you can learn everything there is to know about nuclear physics. There's a lot going on here. And also I'll say, the real reason why this is an active topic of study today is each nucleus is a strongly interacting quantum many-body system with interesting structure and behavior, and each nuclear reaction is a dynamical quantum process. So if you are somebody who spends a lot of time thinking about physics and quantum mechanics and things like this is a fiercely difficult set of problems for quantum mechanics to work on, and it's very interesting. So there's lots of people working on this experimentally, theoretically, computationally. Yes, there's a hand in the chat.
Hi, just curious
Hello?
about these 2 different types of fermions. Is it in addition to bosons or?
Oh,
Okay.
they're protons and neutrons. That's all I mean.
Oh, okay.
Hmm.
Got it. Thank you.
Hmm. Yep. Anyone else? Good question. Thank you for being the brave person to speak up first. Okay, so why care about nuclear physics? So having a detailed understanding of nuclear physics is essential if we want to know about the origin of all the elements we observe in the universe today, as well as how to synthesize new ones. So it's basically understood where the light elements in nature come from, but the heaviest elements in nature, people are still not entirely certain where those come from. astrophysically speaking. There are a lot of ideas, but that's not a fully resolved issue. And the other thing is that the periodic table of elements is still growing. It's often depicted like this, as if this is sort of the end all and be all of elements in nature. And in fact, it's not true. And there are nuclear physicists working on the problem of super heavy element synthesis and trying to figure out if you can build elements that are heavier than the heaviest one on the periodic table here. 118 oganesson was discovered in 2002. So it's conceivable that we can keep going beyond this, and this is a topic of active study. I guess a moderately interesting story. Oganesson fits in the noble gas column of the periodic table of elements. So about a year ago, I asked one of the experimentalists working on this problem, so is oganesson a noble gas? Because, it's conceivable that it will have different properties because the nucleus is so extreme. And she told me that we've produced 6 total atoms of oganesson. So nobody has any idea the answer, whether that's a noble gas. They'll have to make a lot more. Okay, and then another thing which is interesting is what happens in the center of neutron stars. It's believed that there's going to be some wild and extreme physics which is taking place down there. Nobody really knows what's going on. Okay, so nuclear physics is cool. So I'm going to, in a couple of minutes, I'm going to try to give some sense of techniques that you can use to calculate properties of nuclei. So there's a lot of complexity, as I said. Nucleus is quantum mechanical, so you might want to just try writing down the Schrodinger equation and seeing what happens, but that's effectively impossible. So we're going to go over some simpler things first. The nucleus has a bunch of particles. They interact strongly with one another. There's examples of things like this that we're familiar with. One example is liquid. So the first thing that we're going to start with is treating the nucleus as a drop of liquid. And also it's known that protons are charged. So the charged drop of liquid is one of the first sort of approaches that people took to try and understand the behavior of nuclei. This is called the liquid drop model. It was first proposed in the 1930s, apparently. Whoops. Okay, any questions before I dive into the details of this?
Can I just ask you?
Yeah, sure, please.
So you said that each nucleus is specified only by this pair of numbers N and Z. So
Yep.
there are no internal combinations. They somehow recombine in some. There is just one solution corresponding to each N and Z, or there are multiple.
Okay, so you define the nucleus by N and Z, but that doesn't mean that you've reached the end of the story. So you have a bunch of, once you define N and Z, then you have a quantum system with N plus Z particles inside of it. So you can imagine you can heat that thing up, you can whack it in some way, you can put it in an electric field, all sorts of things happen. So they're dynamical and interesting, and I hope to communicate that a little bit here. But yes, you define the nucleus by the proton and neutron number.
So it's a linear combination of some classical solutions or whatever. So like a.
No, it's not that simple. I'll tell you about that. It's not that simple.
I wanted to ask a question also.
Yep, please.
About the equation of state inside the neutron star. Is there
Yeah, sure.
Like how are people tackling this problem? Is this just modeling as of now, or is there an experimental way to probe this?
Yes, so it's an active topic of study. Experimentalists and theorists are working on this. Experimentally, I'm a theorist, so take what I'm about to say with a grain of salt. But I know that astronomers are looking at pulsars because you can get some sort of regular time series of pulses by experimentally looking at pulsars. And there are some ways that you can use that sort of light curve from a pulsar to try to infer the internal structure. That's a whole business in and of itself. And also people are trying to do theory as well to try to figure out what's going on inside neutron stars. And you can go all the way down to QCD, which is like the most fundamental picture of nuclear physics, which is very, very difficult to work with. And then there are sort of a bunch of different layers of analysis that you can work with to try to figure out or basically guess what's going on. And the hope would be that would manifest in some experimental signal that you would be able to observe in your telescope. But people are working on it. It's very, very difficult. I think it's like preposterously difficult to try to work in QCD and figure out what's happening. But in some sense, the answer will ultimately have to come from there.
I see. But for
These
now,
techniques that I'm going to tell you about in a minute here can be used to make sense of the crust of neutron stars, where there's already all sorts of crazy things going on. I'm not going to talk about that, but you'll hopefully you'll be able to get a sense of the kinds of ways that people think about this problem.
okay, thank you.
Yeah, sure. Thank you guys for asking questions. This is great. Okay. Anybody else? Okay, I'm going to charge forward, speak up at any time. Okay, so like I said, we have our nucleus here. We want to make sense of how it's going to behave. We're going to treat it like a charged drop of liquid and see if we can estimate the energy. So what people have done here is they've introduced a formula like this, which basically just says, okay, suppose it is like a drop of liquid. It should have various contributions to the energy. So let me explain what these things variously are. I guess the simplest one to start with is it has some electric charge associated with it. So there should be a contribution due to the electrostatic energy. So Z, we'll recall, is the number of protons we have, and A is the number of particles in the nucleus. So this term looks like a Z squared over R Coulomb term. We have a surface energy, again, A to the 2/3. This looks like an R squared. So there's some surface energy. There's some energy that goes like A, which is the volume of the nucleus. So there's just some energy associated with the entire thing. And then there's this is called the symmetry energy. It's there to try to balance the number of protons and neutrons. And I guess you can think about that quantum mechanically, but that would take us too far afield. And then crucially, there's these A's here, which are parameters that can be fit to experiment. Okay. And if you go through the process of, I guess you would measure a bunch of mass of nuclei and then do this parameter fit, you get some specific numbers. And then you can look at the B over A is this E over A. So I'm sorry, I have mixed notation here. But if you look at the entire nuclear chart, so a bunch of different nuclei characterized by their total number of particles A, and then you look at the fit of this liquid drop formula, you see that you do a reasonably good job. Now, there are fluctuations on top of this, but if you want to get a first impression of what's going on, this is pretty good. Okay. Now, so I guess the procedure here was we said we expect there to be several contributions. Let's just put them in a simple way and then add some parameters, fit them to experiment and see how well we do. This is moderately accurate. It doesn't do so well for light nuclei, but you can still learn a lot. So one example that's relevant in modern day, this is sort of an artist's impression of what's going on inside the fusion chamber at the National Ignition Facility. So if you want to think about the problem of nuclear fusion, they have a bunch of hydrogen that sits inside this little pellet. They bombard it with a giant, world's largest pulsed laser, and they make some big plasma bath, and it fuses the hydrogen together to form helium. The particular reaction is this: you fuse deuterium and tritium, and it gives you an alpha particle and a neutron, and you can, if you're interested in this kind of thing after the talk, you can plug in the numbers here, plug into this formula, and you see that the alpha particle has much more binding energy than the two hydrogens that go into fusing it. So the energy that's liberated in the fusion reaction is the difference there. The helium nucleus is much more deeply bound. So that energy difference is what is released during this fusion reaction. And if you're also curious, you can try this with fission, and you see the reverse is the case. You start with a nucleus that is more bound than the two products. And a puzzle for you, if anybody cares, is to try to figure out where that extra energy goes. Any questions, thoughts about this? I'm going super fast, I know, but hopefully the broad picture is somewhat clear. Okay, so I should probably start wrapping up somewhat soon, right, Xerxes, and switch to hard sphere stuff. I'm just going to take that as a yes. Okay, so nucleus is a fully quantum mechanical object, like I said, so it's kind of not satisfactory to have a fully classical picture of a liquid drop. So the next step would be to treat protons and neutrons as independent quantum particles in some potential. This is sort of related to a question that somebody asked. So the particles are going to be solutions to the Schrodinger equation here, and you want to choose some potential. So a good choice for a potential is something called the Wood-Saxon potential, which looks like this. This is a function of the radial coordinate, so there's some well that the particle can sit in, and then at a certain point it goes to zero. If this is sort of too many details to keep track of, you can also do pretty well with just a 3D harmonic oscillator. This is more accurate, but a 3D harmonic oscillator does pretty well. And if you want to do even better than this, you have your Wood-Saxon potential functional form looks like this. You can add a second term with an L dot S, which is a spin orbit term where you have the dot product between the orbital and the intrinsic angular momentum. And if you add this with the appropriate sign, you can make pretty good predictions for the binding energy of nuclei, which is this E that we were looking at, whoops, on the previous slide here. And furthermore, you can do one thing better. This is sort of a crazy energy level diagram here, but if you just look at the rightmost column, these are the states that the particles can sit in. The energy goes from the bottom of the page to the top. So the idea is you add one particle here, one particle here, one particle here, one particle here, and so on like this. And what if you're accustomed to thinking about these kinds of things, you can see that there are gaps in this spectrum, and these gaps are physically significant because it means if you filled all the way up to this level here, you have to put in a lot of energy to get to the next state here. So this nucleus here will be particularly stable. So if you use this approach of independent particles, you can explain the existence of exceptionally stable nuclei. These are called the magic nuclei. But this concept will be familiar from chemistry for those of you who think about those kinds of things. This is the nuclear equivalent of a noble gas. And the person who first calculated this was Maria Goeppert-Meyer, and it won her the Nobel Prize in the 1950s. Two particles here, this is helium, so helium is the first magic nucleus. 8 particles is oxygen, that's the second one. This is calcium, and at a certain point I start forgetting what they are, but just to give you a sense. Any questions on this?
Maybe how do you come up
question.
with such, sorry.
Okay, no, Pavel, you should go ahead.
Okay, good. Then how do you come up with such a potential? How do you come up with such?
Yeah, so I guess the general picture here, and there's a little bit of a difference from how you typically do atomic physics. So for those of you who have taken a quantum mechanics class, one of the big problems that you solve is the hydrogen atom, right? And you have a 1/r Coulomb potential. You plug that into the Schrodinger equation here, and then you find the eigenstates and the energies. The thing which is happening in nuclear physics, which is interesting, is that in atomic physics, that's an external potential which is imposed from the outside. In nuclear physics, there's no external potential. It's a self-bound system. So the only potential which is keeping everything together is due to the other particles. So in some sense, this picture is unsatisfactory, but the where this potential comes from, and again, you can think about a harmonic oscillator if it's too complicated to keep these things in mind, is you want some sort of potential which binds the nucleus together. So you need to have bound states as opposed to sort of freely traveling plane wave kinds of solutions. And then at a certain point, you introduce parameters. So there's this V0, which is some energy scale. There's this R, which is the size of the nucleus. And then there's this A, which controls the transition from -50 to 0. And this is basically, to answer your question, a guess which fits the broad sort of features of what you would expect. So it has to be negative so that it can bind the particles. If you put in enough energy, you should be able to liberate a particle, which is why this potential goes to 0. But basically, it's a guess where you fit the parameters, and then you see how well you do in describing properties of the nucleus. And if you do a good job, then you stop asking the question of how you're doing. Yeah. Okay, somebody else had 3 more questions, but I think Shraddha, hopefully I'm pronouncing your name correctly.
Yeah, my question was that I had read somewhere that people used to use random matrix theory to calculate this, or rather predict the energy level structure of nuclei. Is that correct?
Yeah, that's true. I think in some sense that's a more advanced approach, and I don't know a lot about it. It gets more sophisticated than what I'm talking about here, but in some sense, this is like the simplest, genuinely quantum approach to try to figure out the spectrum of nuclei. But you're totally right. I mean, if you look at the spectrum of random matrices, which is something that you can do in Mathematica, you just generate a random Hermitian matrix and diagonalize it. I think the idea is, although keep in mind that I haven't worked on this myself, I think the idea is the statistical properties of that spectrum will look like the spectrum of excited states of a nucleus. I think typically a heavy nucleus is the kind of system that is applied to, but I haven't worked on this problem. So if I'm wrong, then you've been warned. That's roughly what
No,
it is.
that's okay. But I was going to ask, is there an intuition as to why this magically the spectrum of the random matrices they produce these excited state structure?
Um, so, okay, in some sense, this question is getting slightly ahead of us, and we don't really have time to go into this fully. But I think the idea is the spectrum that we're talking about in the case of random matrix theory is the many body excitation spectrum of the nucleus. So these are single particle levels that we're looking at on the right here.
Right.
And you can take a different perspective, which is just look at all the excited states and align them. And the premise with random matrix theory, I believe, is interactions, which I'm going to talk about next, although we have to move on here. Interactions introduce complexity into the system, and it's very difficult to accurately understand what's going on there, but you can try to imagine this by just having some fully populated random Hermitian matrix, which means that all the states are transitioning between all the other states, and you just have you have some complexity going on, and just asserting that that would be a totally random matrix. Again, you'll have to forgive me because I don't know a ton about this, but I think that's basically the logic there.
I see. So it's so
Yeah.
complex that you could as well as just model it with a random.
Yeah, and I think that in a certain sense that you have to be only qualitatively correct when you're doing random matrix kinds of considerations. Like you're not going to precisely get the spectrum of lead correct if you have some random matrix or something. But again, more reading for me to do. And I think we should probably move on because there were two more
Yeah,
questions. I
that's
see
okay.
Mohammed has his hand up. Yeah, you're welcome.
Hi, I just got a little confused with your response to Pavel's question. So you're saying that the problem is a little different from the harmonic oscillator because this potential is caused by many other particles, or like, it's the whole system
Yeah,
that's causing the potential. But
yeah,
so I have two questions about this. It's like still the V Wood-Saxon is still a single particle potential. That's like the effective potential that
yeah.
one proton
Yep,
feels or one neutron feels, right?
correct.
Yeah, so how do you account for like, a screening effect or an effect of adding more protons? Like you should expect the energy to change or the potential to change if you have 5 or 6 or 7 protons. Where
Yeah,
does the
okay.
number of protons appear?
Okay, so it's a good point that you're making. This is not a satisfactory picture that I've explained here, because this is in a word, this is a mean field potential, or this is supposed to be an approximation of a mean field potential. So where does this Wood-Saxon come from? The answer is it's supposed to look roughly like the average potential or the average force that a single particle experiences due to the presence of all the other ones. The answer to if you add a proton, where does that appear? So you have this R here, which is the size of the nucleus here, and the R depends on the total number of particles, which is A. So if you added a particle in, then this R changes and the potential will it will move a little bit to the right, this surface. But you can only expect a limited degree of accuracy here because ideally you would compute the actual mean field instead of just approximating it like this. But the idea is that qualitatively the mean field looks something like this potential. And I'll say a
Okay,
little
thank
bit
you.
more
This
about
makes
this, and
sense.
then yeah, I'll say a little bit more in the next slide, and then I know Xerxes is going to get nervous, so we'll move on to what you're actually here for. So I think there's one more question, and then we'll move on.
Just a very quick clarification question. Yeah,
Yep,
the energy splitting diagram on the right, that's not for the nucleus, right? That's
it is.
probably for. Oh, it is. So, I don't understand what's the orbital angular momentum for nucleus. Like that, you have spin orbital
Mhm.
coupling here. Uh,
Yep.
um, yeah, probably I've just never heard of. So can you just tell me what's the orbital angular momentum
Yeah,
in
okay. So I mean, I guess
this?
loosely
Mhm,
speaking, you have a nucleus which is sitting like this. It's some big quantum soup of particles, and the particles are moving around. So
mhm.
there's going to be some orbital angular momentum associated with it. Um, I'm not certain that that's like a deeply satisfying explanation, but maybe another way you can think about this: if you took an isotropic harmonic oscillator, so a 3D harmonic oscillator, you do the usual procedure of splitting into a radial coordinates and angular coordinates. The radial wave functions are whatever they are. And the angular functions are the spherical harmonics, which are going to have those L and M quantum numbers associated with them. So there you go. You already have orbital angular momentum in a sort of a familiar system. This observation of the spin orbit potential was a very crucial observation in nuclear physics. Without it, you get the wrong magic numbers. So you predict the wrong nuclei should be stable. Okay, I promise I'm about to finish. And of course, I'm going to pass over some stupendously complex material very quickly. So independent particle picture, as people have rightly pointed out, I'm glad that you're paying attention. This is unsatisfying because the force between protons and neutrons is one of the strongest in nature. So you can't just pretend it doesn't exist and have a bunch of independent particles. Incorporating interactions into quantum mechanics is a very serious business. This is the kind of work that I do with my PhD. So you have some quantum Hamiltonian here where you have kinetic energy for all the particles, and let's say you have a two-body interaction. In fact, even three-body interactions and maybe higher order are also relevant in nuclear physics. But let's start with two-body. And I'm just going to give you a sketch of how this works. So this is your Hamiltonian. You choose a structure for your many-body wave function. Again, if people have not thought about this, I'm sorry, because this is just way too much to dump on on somebody who's never thought about quantum mechanics before. But for fermions, you need a totally anti-symmetric wave function. So this is a Slater determinant here. Here I've pictured it for two particles, but you can have as many particles as you want inside your Slater determinant. And then what you do is you take this matrix element where you have the Hamiltonian and then their choice of many-body wave function on either side. This is the energy. And then you minimize the energy with respect to the single particle states. Okay. This is a very complicated thing. This is called the variational principle. The quality of your result depends on your choice of Hamiltonian and your choice of state. But the idea being you find some minimum energy solution. And if you do so, you get something like this equation here. This is a Schrodinger-like equation. So you have the kinetic energy as usual. It's for one particle at a time. And you have some regular potential here. You also have some other potential, which looks slightly different because you have an integral here. But the difference being this potential, as opposed to before, which it just has some form, now it depends on the density of the system, which depends on the wave functions. Okay, so this is a coupled system of nonlinear integral differential equations, which is insanely complicated. This is called Hartree-Fock theory. These are the Hartree-Fock equations. And we're basically just going to move right along here. But the idea is if you wanted to do it properly, if you wanted to do it genuine interacting quantum mechanics instead of making a bunch of assumptions as to what it might look like, this is the procedure. You often need a supercomputer to solve problems like this. And this is mean field theory, like I was saying. And if you want to do fission, for example, which is what my group works on, you do something similar to this. Density functional theory is similar to this, except for you don't start with it explicitly with the two-body interaction, because it turns out that you can do better by just guessing a form of a functional, but it ends up being similar. And if you want to, just to give you a sense of the scale of these kinds of problems, this particular simulation here, which is a very accurate simulation of nuclear fission, required solving 4.4 million coupled nonlinear time-dependent PDEs, which was one of the largest simulations ever at the time in 2022, required using more than 27,000 GPUs at once, and it maxed out the biggest supercomputer in the world at the time. Unfortunately, guys, I mean, this is a super interesting topic, but we're pressed for time, and I'm trying to accomplish a bit too much. So I can answer quick questions about this, but we should move on. Okay, so this is how you actually do the problem, but you're trading against really difficult mathematical and computational problem to do so correctly. Okay, so challenges for Wolfram physics before we totally switch gears and talk about statistical physics and things like this. Wolfram model purports to offer a new perspective on quantum mechanics. That's wonderful. If this is right, you should be able to calculate all kinds of things in non-relativistic quantum mechanics. So this would be a nice exercise for somebody to do, and an opportunity to, quantum mechanics has been accumulating results for 100 years. There are lots of results to reproduce, and you can sort of test the efficacy of Wolfram physics in this context. So here are some things that you should be able to solve. 3D harmonic oscillator, you should be able to describe the states and the energies. Try the Wood-Saxon potential. Try adding a spin orbit term. There are the infinite cubic well, infinite spherical well problems. Hydrogen atom, and then, you know, looking at the closed atomic shells, or the closed shells for nuclei and atoms. So, you know, 3D quantum mechanics is a great opportunity for people to take a look at and see if you can reproduce these results. And maybe you can even do better. Maybe you can do a full interacting many-body system of this kind. That would be fantastic, and people would be very interested to know if you could just fully simulate an interacting many-body system and determine the ground state energy or something like this. Okay, so that is a provocative suggestion for you, and I will leave that to you. So now we're going to totally switch gears and never talk about nuclear physics again. So if you have any last questions on nuclear physics, let's discuss them now. Are people somewhat interested? Is this an appropriate sort of pace? And okay. All right. If you have questions, if you have comments, speak up. Okay. So now we're going to totally switch gears. We're going to talk about hard spheres. Like Xerxes mentioned, this was something that I started in 2020 with the Wolfram Physics Project. We've been working on it since then. We're in the process of writing a paper, so that's exciting. Okay, so let's talk about hard spheres. So before I do anything, let's just play a movie. So this is the absolute simplest bit of physics for hard spheres. You have some circular particles, in this case in 2D. They move along straight lines, they bounce off one another. The way that they bounce is determined by the fact that the particles have extent in space. At the bottom here, we have sort of a gas state of these things where they're all bouncing around inside of a box. Okay, so hopefully this is clear what we're talking about. We're now talking about classical gases, which in some sense is a much simpler problem than the interacting quantum thing that we were just talking about. So hard spheres are sort of a prototypical model of a non-ideal, which is to say interacting gas or liquid. They interact through a short-range repulsive force. This is the pair potential on the right, if you're interested in this kind of thing. This is probably the longest studied interacting many-body system in all of physics. It goes back at least to van der Waals, which is in the 1870s, so this is a 150-year-old problem. They were also crucial in the early history of computational physics. There were simulations done by Alder and Wainwright in the 1950s of hard spheres in 2D and 3D, and van der Waals won the 1910 Nobel Prize for his work. This might be sort of a laughably simplistic model. So it might be surprising for those of you who don't know about this, that this is still widely used in modern condensed matter physics, primarily what people would call soft condensed matter physics as opposed to hard condensed matter physics. There's a lot of surprisingly rich physics to this system, primarily in the sense that it undergoes a variety of phase transitions under different circumstances. So as you go to very high densities, you can have a solid, a glass, a hexatic, which is a particular phase which only exists in 2 dimensions. And there's something called the Gardner transition, which is very interesting, but I don't know a lot about it. And there's phase transitions associated with each of these different phases. Also, for those of you who are mathematically inclined, as I know many of you are, sphere packing problems are widely studied in modern pure math. There was the 2022 Fields Medal, which went to Wiazowska and maybe somebody else on finding the densest packing in 8 and 24 dimensions. There was also the Kepler conjecture, which was conjectured in like 1605 or something and was finally proved in 2017. So these are very difficult problems. There's also high dimensional sphere packing is relevant for error correcting codes. So there's a lot going on here, even though it looks very simple. Okay. Whoops, let me go to the next slide here. You can also realize hard spheres experimentally in colloidal systems. The idea is that this interaction is a highly simplified model of forces between atoms or forces between molecules in liquids and solids. Still very useful. Although simple, the theory has no free parameters and it can be solved exactly. So if you observe a phenomenon in this system, it's not like it depends on, you finely tune some detail of the system relative to some other detail of the system. It's just it's very simple, and there's a lot of phenomena. The question of whether those phenomena will necessarily be revealed in nature is a separate question, but there are advantages to working with simple theory. This bullet point here is sort of silly. If you contrast this with the standard model, which has 19 free parameters, or in nuclear physics, we work with at least 9 free parameters or something like this. We have no parameters at the cost of, it's a simplified thing. So that's silly, and I probably should have deleted that point, but anyway. Okay, so this is the basic setup. Do people have any questions about what it is that we're going to be talking about? Like, what are hard spheres, basically? chime in at any time. Okay, so let's talk about the basic physics that you can do with this. Suppose you have some simulation of hard spheres like the kind we were looking at on this slide. They bounce around inside the box. Okay, what do I do with this information? So the simplest thing that you can look at is the distribution of speeds or the distribution of velocities of the particles. And if you do so, you'll see a histogram like this. Here I'm looking at the distribution of speeds. This is a Maxwell-Boltzmann distribution. The functional form of this thing is like this. And where does this come from? So this is the maximum entropy probability distribution with the additional condition that the average energy of the system is fixed. So I have the sort of mathematical expression of this idea. So I have some probabilities pi, which I want to assign to the various speeds that the particles could take. I calculate the entropy, which is like the disorder, by this formula here. And then I add some Lagrange multipliers. The distribution has to be normalized. And also there are some energies associated with these. And I want the average energy to be some fixed thing, expectation of E, which I provide. And if you minimize this, you get this probability distribution here, which you can see is a good fit for the histogram, which comes from a numerical simulation of a hard sphere system. By the way, this figure was made with hard sphere simulation, which is a function on the Wolfram function repository that came out of my 2020 summer school project. So you can go play with it. It's pretty easy to use if you want to toy around with hard sphere systems yourself, which can be kind of fun. A few more things to say. The temperature in the hard sphere system is just given by the kinetic energy in the equipartition theorem. So this is the relevant formula. And the only energy in the system is kinetic energy. So there's no other energy due to interactions. Any questions about this? Okay, so now we have something that we can say about an aggregate of hard spheres, a hard sphere gas. Okay, so now let's talk about spatial structure. Okay, so you might imagine at very low densities, you might just have like totally random distribution of particles, but at a certain point when the density gets high enough, that's no longer going to be the case because they can't overlap with one another. So the effect of the overlap is going to start to become important at high densities. There's a simple way to quantify this. It's this object here, which we call G of R. This is called the radial distribution function. And basically what you do is you take a histogram of all pairwise distances between the particles. So if you look in this little inset, we have a frame from that simulation we were looking at before. Fixing our attention on just this one particle here, you can look at the distance to all the other particles. And then you can repeat this for all the other particles in the simulation. You get some histogram, and then if you normalize it in a particular way, you get this function G here. So here's how to interpret this thing. G of R equals 1 corresponds to total randomness. So if you just took random points in a plane, and then you pass them into G of R, you would get 1 with some small fluctuations on top of it. G of R greater than 1 means that you're more likely than random to find a particle, two particles separated by distance R, and G of R less than 1 means you're less likely than random to find two particles separated by distance R. Okay, so if we take a look at this picture here, this phi is the density. So red is the least dense system, green is slightly more dense, orange is more dense, and blue is more dense than this, but still these densities are pretty low. And a couple of things to notice. First of all of them go above 1. So you're more likely than pure random to find two particles separated by about 2 radii between them. So that's slightly surprising, right? You might expect it to be 0 out to 2 because they can't overlap, and then beyond that, pure randomness. But what we see is, in fact, as the density gets higher, it's increasingly likely to find them right up against one another. And then it is less likely, and then it is more likely and less likely, and so on. Yeah, Mohammed.
So I kind of understand the exponential decay, like the modulation of the decay as a function of R, but I don't understand the oscillation. Like, do you have an intuition why is it oscillating as a function of
Yeah,
R?
sure. It's yeah. So imagine that you have two spheres which are directly next to one another, so they're touching, right? So that would correspond to R equals 2 radii, and then the next place that you could possibly put a sphere is 4, right? So if you
I
have a
see.
sphere here, you can't put another one inside of it. So that's why there's a peak at 2 and a peak at 4 and a peak at 6 and so on.
Mhm.
So that's
Okay.
they're aligning. Okay. Now, I'm going to say a little bit about this, why it is that there appears to be an effective attraction between the spheres, because you're more likely the random, even at high density, you're likely to find them touching right up against one another, which is slightly surprising. But just a note that if you accurately determine this function g, you can use that to calculate the equation of state, which is like the extension of the ideal gas law, the pressure versus the density for this system. And one more thing for those of you who are observant, it should be probability 0 that you find the spheres less than a distance of 2 radii away from one another. But this function has a support inside r equals 2. That's because I made this with very little data and I used a smoothing function. So don't take the details of these curves too seriously. Like, this is unphysical, the fact that the function is non-zero inside r equals 2, just in the spirit of full disclosure. Okay, any more questions about this? Okay, so where does this effective attraction come from? There are sort of two perspectives of this. One of them is that if you imagine some configuration of spheres in space like this, and they're being bombarded from all sides by the other spheres in the gas, you can see that there's an asymmetry here, because there are more ways that a randomly bouncing sphere can push the particles together than there are, ways that randomly bouncing particles can push the spheres apart. So this is one interpretation of where this effective attraction comes from, even though there's no attraction in the pairwise sort of force between the particles. And another perspective, which would take a little bit longer to be fully convincing of, is this notion of excluded volume. For those of you who have thought about statistical mechanics before, the volume of a sphere obviously just extends to the edge of the potential here, but in fact, there's a larger region here, which is associated with the closest distance that another particle could approach. And it turns out the entropy of the system goes like the total volume available for the spheres to move, and the total volume is actually larger when the spheres are close together. So this is an excluded volume argument. Okay, so that's where the attraction comes from. Questions?
Yeah, sorry. Why is the volume larger when the sphere are closer? I just can't intuitively see it.
Yeah, so it has to do with the difference between these black circle, which is the particle itself, and this dashed circle here. And okay, so the essence of the argument is that if the spheres are close together or touching, then the area inside these dashed regions can overlap, and the sort of free space available to the system, which is not inside of any dashed circle, is larger. Why is the dashed circle the relevant thing? If you think about hard spheres as point particles for a second, and you try to bring them together, in fact, the closest distance that they can approach is 2 radii, and that's what this dashed circle is. So it's the closest that the center of another particle could get to any given particle, and that's what determines the amount of free space. Determines the entropy. It's a bit of a complicated argument, but when you work it out in detail, you see that this is how it works out. But if that's not satisfying, just think about this. Okay. Anyone else? Right. So now let's talk about phase transitions here, just seeing how I'm doing on time. Okay. So roughly speaking, a phase transition is some discontinuous change in the system in response to a small change of some control parameter. So the simplest phase transition is the liquid gas transition, also known as boiling or condensation. These are analytical results due to van der Waals in the 1870s. I've already mentioned him. And these results are significant primarily in they were crucial in establishing that atoms and molecules actually exist. So again, even 150 years ago, a lot of people were not convinced that atoms and molecules actually exist. Everybody knew, of course, about water and about water vapor. If you boil water, it disappears. But some people thought that was some sort of chemical reaction, and something was not simply physical was happening. And van der Waals, his model was crucial in establishing the existence of phase transitions. Okay, so In order to understand this, you look at a sort of modified potential here. So again, this is the energy of interaction between particles as a function of the separation between them. If you put them close enough that the energy is infinite, this is the hard sphere potential that we've been talking about. But you add an additional term. This is a long-range attractive force. People have heard about van der Waals forces. This is roughly what they're referring to. And this is the functional form of the van der Waals interaction. And if you do this and you crank through the usual statistical mechanics machinery, you go to the partition function, and you make some low density expansion, you can calculate the pressure as a function of the number of particles and the size of these particles. And that's this function down here. This is known as the van der Waals equation of state. For those of you who have seen the ideal gas law, as I expect many of you have seen, maybe it's been a while since you thought about it, the pressure goes like the number of particles, kBT over the volume. That's the ideal gas law. And we see that we have something like the ideal gas law, excuse me, but modified in a way. So there's some term here which depends on the size of the particle, which increases the pressure, but there's also a second term with a negative sign, which decreases the pressure. The second term is due to this attractive interaction. Okay, so this is known as the van der Waals equation of state. And what we can see is we can look at the pressure versus the volume as we lower the temperature of the system. And as the temperature gets low enough before some critical value, there's a non-monotonicity that occurs in this curve, which can be understood as a competition between the first term, which relates to how the particles are sort of pushing away from one another in this hardcore interaction, and the second term, which is an attractive interaction. And if you have this, these two terms become similar in magnitude if the temperature is low enough, so you get some competition between them. What this means, if you look a little bit more closely, is that at a given temperature, your system is in equilibrium. You can have multiple different equilibrium states at the same pressure, which is slightly surprising. And now there's a bit of a question as to what to make of these things. So first, let's focus on this middle term here. Again, this is pressure, this is volume of the system. So let's imagine that we decrease the volume of the system slightly and that would push this point slightly to the left. And what you see is that if you decrease the volume of the system, you squish it, then the pressure decreases. And similarly, if you were to increase the volume of the system, then the pressure will increase. You expand it and the pressure increases. So this is characteristic unstable behavior. So this middle equilibrium point is in fact not physical. But if we look at this point here, if we were to compress the system, then the pressure will respond very rapidly and will increase. So this is a very incompressible state of matter down here. And over here, if you compress the system, then the pressure barely responds and you can compress it easily. So van der Waals' insight was that this state on the right here is basically a gas-like state, and this state on the left here is basically a liquid-like state. And the middle state is unstable, as I said, and these two phases can coexist with one another at the same pressure, and they often will phase separate into bubbles. Yeah, go ahead. Question.
So my question was that if you take this equation and rearrange it a little bit, right? So it'll be P plus n squared over V squared times V minus Bn. So, and that would be equal to n kBt. And the ideal gas equation is PV equal to n kBt. So seems like in this effective equation, the volume is lower, but in the previous slide, we said that the effective volume is actually more. So what's up with that?
Oh, okay. So you're talking about the entropy discussion and the excluded volume thing that I was talking about. Yeah, so those are two slightly different things. In this case, the V is the total volume of the system. Like literally, if you have a cube, it's just the side length of the cube cubed, let's say. Whereas the volume in the discussion of entropy back here is a slightly different thing. It's the volume of available phase space. So in fact, it is less than L cubed. Sorry, I just said something that was incorrect. It's an n-dimensional phase space. So for an ideal gas, that volume in question would be the volume of the system to the power n, where n is the number of particles. But in fact, for this interacting system, the excluded volume is less than that because you can't just put the particles anywhere. This point about excluded volume is not going to come up again. So maybe I shouldn't have included it all because it's kind of confusing. But it's more important to understand that this V here is just the volume of the system. Does that make any sense?
Yeah, just need to think a little bit more about this, but thanks.
Yeah, the excluded volume bit is not going to come up again. So if it's confusing, feel free to just throw that knowledge out, and the rest of the talk will proceed just fine. Okay, we have another question here.
Hi. So the emergent attraction between the hard spheres and the van der Waals attraction, which goes as 1/r⁶, these are two different sources of attraction between hard spheres, right?
Totally different. Totally different.
Right.
This
Yeah,
this
just
1/r⁶ is an additional piece that I'm adding as a way of illustrating phase transitions, because we're going to talk about phase transitions in hard spheres, but this is not a hard sphere model. This is a hard sphere plus an additional thing. And if you want to know where it comes from, there's some argument about a fluctuating electric field in one atom induces the polarization in the other, which is then attractive, whatever. That you can argue that goes like 1/r⁶, but this is not a hard sphere model.
right. But can one make similar arguments that because like you can have a similar corrected ideal gas equation for the hard spheres as well, which looks like this, because even there you have an attraction term and a corrected volume term. Is that correct? Can you have
so yes, what you're asking about, so this is the van der Waals equation of state. You're asking about the hard sphere equation of state. That is going to figure prominently in the rest of this talk. And in brief, the story of the hard sphere equation of state is there are various analytical ways that people have been trying to calculate it, but nobody knows the hard sphere equation of state accurately, and most of the results are numerical. But that's what we're going to talk about soon. I want to set up these phase transitions because we're going to talk about a bunch of different phase transitions for hard spheres going forward, and I want people to have some frame of reference here. Sorry about that. These are good questions. Anybody else? Okay. Yeah, so basically, yeah, this is the story of phase transitions in the van der Waals model here. So now let's talk about the hard sphere equation of state, exactly as we just said. Okay, so in some sense, the picture is a little bit simpler, although it is definitely analogous to what we were just looking at. On the horizontal axis of this figure here, we have the density of the system. So all the way left, this is completely dilute. You have point particles. All the way right, you have here this point, which is FCC. This is a face-centered cubic lattice, which this is the so-called Kepler conjecture that I mentioned earlier, is that this has been proven to be the densest possible packing of regular spheres in 3D. So we are increasing the volume fraction, which is equivalent to the density, somewhere between they're infinitely small and they're as dense as they can possibly be. And when we do this, we see that the pressure increases for a while, and then something interesting happens, which is labeled by freezing and melting on the horizontal axis, where the density continues to increase, but the pressure stays exactly the same. And then at a certain point, the pressure increases again. So down here, we have some sort of fluid, gas, liquid-like phase here. Then once we reach this point here, at this left point here, you have a fairly dense fluid, and then at this right point here, you have a fairly not as dense as possible crystal. And then these things sort of slowly transform into one another by some sort of seed of crystal will grow here, and then the fraction of the liquid, which is crystal, will slowly increase as you move across until eventually you have a crystal. So the idea is down here you have a liquid, and maybe in here you have a liquid with a bubble of crystal inside of it, or a nucleus of crystal inside of it, and by the end you have a full crystal. So this is the freezing/melting phase transition, depending on which way you cross that gap. And then once you're in the crystal phase, the pressure just continues to increase until at a certain point you reach the maximum packing of spheres and the pressure diverges. But there's also some interesting stuff which happens up here as well, which is that you can extrapolate this liquid branch of the phase transition. So if you don't allow the system the opportunity to cool, you can get what's called a metastable liquid, where you can get a disordered liquid kind of state, which you can continue to have up to very high densities. And then at a certain point, I should indicate that once we reach here, people are actually not entirely certain what happens. But there's some speculation that some sort of phase transition to a glass-like state, which is an amorphous solid-like state, must take place, because of what is known about liquids. If you extrapolate this, the pressure diverges at way higher densities than it's supposed to. Like, you won't even have an infinite pressure beyond the dense sphere packing limit. So that doesn't make any sense. So people have speculated that some sort of glass transition will take place up here. And in fact, as you take the spatial dimension of the system to infinity, which on surface might be a strange thing to do, people have demonstrated conclusively that a glass transition does in fact take place. The question of d = 3 is something that people are still working out, and we're going to be talking about glassy states of hard sphere systems as well as crystalline states of hard sphere systems for this topic, or for this talk, excuse me. And just note that because there's not an explicit attractive interaction, we've talked about this, hard spheres technically do not form liquids, because that van der Waals phase transition we just discussed does rely on an explicit attractive interaction for that phase transition to occur. Okay, any questions about this? Is the hard sphere equation of state at a qualitative level. And what we're going to do is we're going to do our own studies, and we're going to vary the density. We're going to look at this kind of glassy phase. We're going to look at these crystalline phases, and we're going to look at the low density stuff as well. Okay, so talk a minute about simulation techniques. Again, just looking at my time here. So there are two primary techniques for simulating systems of hard spheres. You can do a Monte Carlo, which is very easy, which is basically you throw the spheres down in a box, and then you just move them randomly. And as long as they don't overlap, then that's another valid move. And you can use this to study equilibrium properties of hard sphere systems at any density. If you're a computing kind of person, you might be interested to know that these techniques are amenable to GPU acceleration and parallelism. And the accurate determining of this equation of state, it turns out, can be numerically quite intense. Not quite as bad as those crazy system of coupled equations we were talking about in nuclear physics, but still a serious enterprise. And you might need your GPU to get very accurate statistics for the pressure. The other technique, and the one that we're going to talk about today, is molecular dynamics, which is where the spheres are actually moved on straight lines, and when they collide, they bounce off one another. The way that they do that is dictated by momentum and energy conservation. And if you work it out, you can see that the velocity update rule is as follows. So you have your two spheres, they've just collided with one another, and they're sitting, touching one another. What you do is you take the velocity vectors of each sphere, you decompose them into the component which is along the line connecting the centers of the two spheres. And perpendicular to that line, and what you find is that perpendicular to that line, the velocity components are unchanged, and parallel to that line, they swap with one another. So the implications of this, we could look at two limiting cases. If you have a head-on collision where this particle is coming in with a certain speed and the other one comes in with a certain speed, those velocities are just exchanged between the two particles and they bounce off one another. Whereas if you have a completely glancing collision where they just barely skim past one another, the velocity components along the line connecting the spheres are zero, so the velocities are unchanged. And then if you have an intermediate case, this is the rule. You can use this to study non-equilibrium physics, which is what we're going to do. It's a bit too much detail now to say that you can work out exactly the time that the collision will take place. That can be used to make your simulations go very quickly. And in fact, this is necessary because you can't parallelize simulations like this. People have tried, and it's not the best way to run really efficient simulations of systems like this and really accurate simulations. But what you can do is you can use things like binary search trees and domain decomposition, which is pictured here, where you divide the box into little cells, and then you only have to look at what's going to happen around each particle. So there are ways to accelerate this. And I mentioned this already, but if you look up resource function hard sphere simulation, you can play around with the simulation for yourself. It's using a crude version of molecular dynamics. We have more accurate versions for the results I'm going to be reporting on now. Okay. So what does any of this have to do with Wolfram physics? You've been patiently sitting here for over an hour, and I've only brought up Wolfram physics once, and it was in the context of nuclear physics. So let's talk about that a little bit. By the way, before I move on, do people have any questions or cares about simulation methods? A little bit in the weeds. Okay, so we're going to try to connect to the Wolfram model by way of causal graphs. Like Xerxes was saying, this is rather than being sort of fundamental physics, this can be thought of more of as an application of the tools of the Wolfram model to more pedestrian kinds of physical systems and see if they can offer some insights. So we're going to try to connect by way of these causal graphs here. So I've illustrated. I have an example here. It's not clear how illustrative this is, but anyway, we have some sort of string substitution system where we start with some initial condition, and then we have some rule here to update the system. This is a multi-way system, so we see that we apply the rule in one way here, we get this string. If we apply the rule in another way, we get a different thing, and then we can apply it in multiple ways and so on. And this sort of enumerates a number of various paths through the system. And you can see that this graph here has two different kinds of nodes. There's the nodes associated with the state of the string, which are in blue, and then there's the nodes associated with updating rules, which are in orange here. And what you can do is you can connect the updating rule events together if one is in the causal future of the next one. So this updating rule is applied, and that gives some state, and then that state is further transformed. So these two updating rules are connected because they happen in sequence with one another, and so on. And those are the orange vectors in this picture. And then if you just throw away the states and look at how the updates are connected with one another, you get this causal multigraph object here. Now the question of what you do with something like that in the context of a string rewriting system, I'm not the right person to ask, but this is an example of a causal graph of the kind that we encounter in Wolfram physics. Any questions about this? I'm just using this as an analogy. We're about to introduce it for hard spheres. Okay, so we're going to introduce it in the context of hard spheres, and actually the causal graphs will turn out to be simpler than in this multi-way system, because we do not have a multi-way system. So basically the idea is an event in the context of hard spheres is going to be associated with a collision. So the system evolves from collision to collision to collision. Each one of those collisions is going to be an event, and that's going to correspond to a node in our graph. Okay, so an event looks like this. You have some particle, particle I, some other particle, particle J. They collide at some time t0. So nodes are events, and this is extracted directly from the time evolution of the system. And then edges in our graph are going to correspond to particles. So they connect collisions which involve the same particle. So here we have some collision between particles I and J at time t0. Then we have another collision between particle K and particle I. Again, the order of these two arguments does not matter. At some later time t1, so these both involve particle I, so they're going to be connected by an edge. And the rule is that you only connect adjacent collisions in time. So if particle I goes off, collides with particle J, then K, then L, then the connections look like this. So particle I goes from this collision to this collision, and then this collision and this collision, but it's not transitive. You don't link them up in that way. Okay, so does this construction offer any physical insight? It's an arbitrary construction at this point, so I expect people are not perfectly following this. But the situation is like this. We have basically a Newton's cradle with periodic boundary conditions. That's the setup to introduce this thing. Sorry about that. And the causal graph that we extract from this is pictured to the right here. So what you can see is that every vertex of the graph is labeled by a triple of numbers, which again is the identity of the particles and the time at which the collision takes place. And they're joined up if one particle is involved in two adjacent collisions. So this can be made slightly clearer if we add some color to the causal graph. So like I said, all the collisions all the nodes correspond to collisions, and then the edges correspond to particles. So it's helpful if we just sort of choose a color and follow it through the graph. So let's choose green. So we start with particle 2 and particle 3 collide at this time, and then we follow the green edge. We have particle 3 and particle 4 collide at this time. So that means that this edge corresponds to particle 3. All the green edges will correspond to particle 3. So we follow particle 3 down here, and then 3 collides with 2 again at some later time, and then 3 collides with 4, and 3 collides with 2, 3 collides with 4, and so on. And you can work your way through the graph using these colors as a way of sort of identifying what's going on here. Okay, it's an arbitrary construction, but is it somewhat clear what it is that we're looking at here?
I have a question. So when you say like particle 1 is colliding with particle 3, so is there anything special about particles 1 and 2 colliding with each other, or are you just starting a random event and seeing what follows from this?
No, so what we're doing, there's nothing special about them. What we're doing is you have some simulation. I'll go back to the previous slide. If my computer would let me go back. You have some simulation like this, and at the starting time, you just label each particle. So the particle on the left, I mean, here, let me freeze time for a second. The particle on the left, this is particle 1, this is particle 2, this is particle 3, this is particle 4, this is particle 5. You time evolve the system. In this case, it's just some simple thing like this. And then the causal graph can be constructed after the fact from this by just keeping track of who collides with who.
Okay. Makes sense.
Okay, so this is an arbitrary construction, right? At this point in time, you might accuse me of just constructing something for the sake of constructing it. We want to see if we can get some physical insight from this, and we can. That's the story that I hope to tell, I hope to convince you of going forward. Are there any other questions? Okay. Okay, so that's the causal graph. Now the reasonable, okay, so let's talk about basic properties, but we should keep in mind, like, is this actually useful for anything, or is this just something to construct because we can? So one thing that is useful about this is the causal graph is invariant under a large group of transformations to the underlying system of spheres. You can translate it in space, you can rotate it, you can reflect it about the origin, you can translate in time, you can in fact Galilean boost, so all the particles are given some additional velocity in the same direction. And the causal graph is exactly the same. This is just a basic consequence of Newton's laws not caring about those kinds of transformations. So any information that we can extract from the causal graph will not depend on that kind of transformation to the underlying system of particles. So maybe we can hope there's some promise that this could be a useful way of encapsulating information about the system. From a mathematical perspective, the in degree and out degree of each node is going to be 2 apart from nodes and the boundaries. And it's a directed acyclic graph. It's not necessarily connected, but if you run the system for long enough, it will end up being connected. And then every new collision adds a node, right? So that means that if you take a large system or you run it for a very long time, the causal graph will be an infinite structure. Okay, so these are just basic sort of properties of what to expect from this. Okay, so now the question is, can we use the causal graph to do physics? There are 2 basic kinds of quantities that we can look at in the causal graph. Well, I mean, there are many, but there are 2 useful kinds of quantities to look at the causal graph based on my experience thinking about this object. There are paths through the causal graph. So you start at some node, you go to the next node, you go to the next node, you go to the next node, and so on. And then there are light cones. And we'll talk about light cones in the next slide. So let's talk about paths first. So we recall, based on 2 slides ago, that particles correspond to paths in the causal graph. So like one color is the same particle over time. Really sorry about the coughing here. Like I said, recovering from a cold. Okay, so particles correspond to specific paths through the causal graph. And looking at each path in isolation, we just see a sequence of collisions. So the obvious thing that you can do from that is construct a collision rate from a sequence of collisions. If you like, you can think about the collision rate as a foliation of the causal graph using sort of Wolfram model type language into bins and then counting the number of nodes in each bin. But otherwise, you can think about it as just sort of a standard collision rate. we've been talking a little bit about the pressure and therefore the equation of state. And it's interesting to note that the collision rate is related. There's some affine transformation between the collision rate of the system, which is this gamma, and the pressure. Okay, so if we can determine the collision rate, we can determine the pressure. One advantage that the collision rate has is that it can be used as a measure of both equilibrium physics by calculating the pressure, but also non-equilibrium physics of the system, because you can calculate at equilibrium at a certain density, and then you can calculate the collision rate if you whack the system in some way, you perturb it in some way, and then you can see that it will do something until it eventually settles down to equilibrium or does not. And that's the kind of study that we're going to do here. So the collision rate is going to be our way of doing both equilibrium and non-equilibrium physics using the causal graph. But this last bullet point here is to really note, it's not using the causal graph sort of to the fullest extent, right? This is going to be starting with the causal graph, extracting a particular path through it, and then taking a look at the information that what this path has to offer. We'll come back to the question. Well, actually, we'll just go to the next slide now. We'll talk about this. Oops. Okay, so this doesn't really utilize the structure of the causal graph in a fully satisfying manner. If we look on the right here, we have what I'm calling a light cone. This is a light cone in air quotes, and I'm going to be loose with the air quotes throughout the rest of the talk. This is the light cone on the causal graph. So what you do here is you start at a particular node, and instead of just following one node at a time, you follow all edges out from that node. Those reach nodes, you follow all edges out from that node. And in this way, you trace out a subgraph of the full causal graph, which is incorporating much more connectivity information. And this is analogous to a light cone in the sense that the sort of causal future of any given collision, because remember each node is a collision, is contained in this light cone. So a collision takes place, then those particles fly off, they get involved in collisions, those particles fly off, they all get involved in collisions. The sort of the implications or the consequences of that initial collision and the propagating collisions are what is captured in this light cone here. Light cone in air quotes. So let's see. Yeah, these structures will primarily be useful because they allow you to observe the propagating effects of collisions through the material, especially at high densities. So the number of particles in a light cone after a given amount of time will be related to the speed of sound, and you can also look at the spatial structure. We'll talk about this. But I also want to give you an indication of the kind of study that we're going to be doing. So on the bottom of the page here, we have a bunch of hard spheres, and we're increasing the density as we go from left to right. So that's the relevant control variable to the system. There aren't really that many knobs that you can turn to try to get something interesting happening apart from the pressure. Excuse me. So that's what we're going to do. We're going to increase the density, and we're going to look at these kind of causal graph inspired quantities, and then we're going to see what happens. Okay, are there any questions about the general setup? So we have paths, we have light cones. We can use paths to get the pressure and things like this. We can use light cones to get well, we'll take a look at what we could learn from them, but we can also learn some things about them.
Can you talk for like a little bit about the equation relating the pressure to the rate of collisions? And
Sure.
what is yeah.
Okay, so I guess it's probably easiest to think about the pressure as, let's imagine you have a box with hard walls. Okay, so you have reflecting boundary conditions, particle comes towards the wall and bounces off. The simplest understanding of the pressure is just you accumulate each time the particle bounces against the wall, it imparts some force to the wall. Force divided by area is the pressure. Okay. So you imagine some very dilute system of particles where they're basically just point particles, they're not interacting with one another. There will be some rate at which the particles bounce off the wall and then they go about their business. That's going to be associated with some pressure. Now you imagine blowing up the spheres to the point where they're really big and they're really interacting with one another and getting in the way. Now, let's say you have some very dense configuration like this one on the right here. And you imagine you take a look at one of these spheres close to the boundary of the box. That sphere is just going to do nothing but rattle back and forth between its neighbors and the wall. So that means that the number of collisions being imparted to the wall in any unit of time is going to be much higher for the case where you have a dense system, compared to when you have like an ideal gas of just point particles moving around. So
Makes
in that
sense.
sense, the pressure is going to be related to the rate of collisions inside the box. Now, for that construction, I invoked a hard wall, but it doesn't really matter, right? You can just imagine that if you have some situation like this, but you have periodic boundary conditions, so all the spheres are just trapped in against one another, they're going to be pushing very hard on one another. And the relationship is you have some, it's basically, it just goes like the collision rate. The details of this are not super important. The
Okay.
point just being, if you have, excuse me, if you have the collision rate here, these are just some quantities that are related to the system. You can calculate this PV over NKT. It's important that you divide by the temperature, because you imagine you increase the temperature, then you're going to increase the pressure. That's even true for the case of the ideal gas. But if you normalize like this, the collisions are capturing the additional degree to which you deviate due to the hard sphere interaction.
Okay. I was just like meaning what is gamma and what's gamma not, but like as you said, they are not relevant, so we can skip this part.
Oh no, I mean I can tell you what this is. This gamma is the collision rate of the system. So you have a bunch of particles in a box in 3D. They evolve in time, they bounce around off one another. This gamma is the total number of collisions divided by the total amount of time of the simulation.
Okay.
Gamma naught is going to be some reference value. So it'll be that same quantity, but if you took the same simulation and you set the size of the particles to 0,
Mm-hmm.
so it's all the collisions that happen. Okay, I guess what I just said is not quite right, but you should think about this as being like the ideal gas sort of limit of the same quantity. So it's some reference collision rate. This is the actual collision rate. This V is the volume, and this B is the second virial coefficient, which is not worth going into.
It's okay, I get it. Okay.
Can
Anyone
I just
else?
ask a
Yeah,
funny
please.
question? So you said that are simultaneous collisions allowed? Like for instance, if if there is one particle sitting and two particles bump into her at the same time, so you have two collisions events. And from some previous collision event for the middle particle, you would theoretically have to, for this one particle, would have to put an arrow to both of these events. But in the previous collision event, another particle was involved, so there is only one, so it would be like three output edges.
Yeah. So the answer is you can certainly set up situations in which that happens, but those situations all have a certain amount of symmetry associated with them. So the simplest situation where you just have three particles arranged in a line, and then the middle one has velocity 0, the other two have velocity like +1 and -1, let's say. They come in, and then you have a genuine simultaneous three-body collision. But that's a situation with symmetry. I mean, what you will quickly convince yourself of is that if you don't have a symmetrical system, that's a probability 0 occurrence, and they just never occur. And in fact, since we're calculating the time of collisions exactly, and we're not using some approximate scheme, which means that we're using double precision numbers, we have 16 digits of resolution for time. It just does not happen. So you don't need to worry about it.
Okay, thank you.
Yeah, we thought about this, and it's a huge mess if you try to work out what happens with simultaneous collisions. But mercifully, for situations of interest that don't have symmetry, they do not occur. Anybody else? I hope people are still with me here. As I predicted, everybody has webcams off. Okay, except for one person now. Thank you. So I'm speaking to the void, and I can't tell if people are interested or following or anything, but I'm going to keep talking one way or another. Okay. Okay, so let's talk about the collision rate. As I said, so we know that thank you, everybody. This is much nicer. So as I said, actually, I reproduced the equation here. If we know the collision rate of the gas, then we know the pressure of the gas. So let's just work with the collision rate because we know we can also get the collision rate from the causal graph, and we want to use the causal graph for the study. So we're going to define gamma as the average number of collisions per particle between time t and t plus dt. It's the collision rate, single particle collision rate. And then we're going to run a simulation as a function of time, and then we're going to choose a bunch of different densities and do the same thing. So this is our starting point for this study. And what we can see is these things are basically constant with small fluctuations around some constant value. Okay, so these are simulations at equilibrium. We can see that the time dependence is just evolving from one equilibrium state to another equilibrium state. We have small fluctuations, okay? Is it clear what we're looking at here? This is going to be a baseline for more interesting sort of experiments that we run. Okay, so now so I guess the first thing that we might want to do is we might want to just take the time average of each of these curves, and then we get here, this is the density. This is the average collision rate. We get some curve that looks like this. If you swap out this gamma for the pressure, you see we have the pressure, which increases as a function of density. Then we get some loopy sort of non-monotonicity, and then the pressure increases. Hopefully that will be reminiscent of the discussion of the van der Waals equation of state that we went over earlier. Okay, so these vertical dashed lines here are indicating values that other people have reported in the literature as to where this phase transition actually occurs. It looks like our phase transition might be shifted to slightly higher densities, but they probably have better statistics than us. It's not super important. The point being, we have some fluid at low densities down here. We have some crystal at high densities, and there's some transition region between the two of them. So we run hard sphere simulations at various densities. At a certain point, you crank up the density high enough, you get a phase transition. Okay. Let's see. So that's equilibrium behavior, but there's not that much to say about equilibrium behavior apart from this. This is sort of the equation of state according to our simulations. So let's do something more interesting. This here, what we're going to do is we're going to perturb the system in a certain way and then see how it relaxes to equilibrium. This little inset here is a very crude illustration of what we're going to do. We have some system of particles. In this case, I guess they're arranged in some regular configuration. And then what we're going to do is we're going to heat up just a region in the center, and then we're going to let the system evolve over time. And that's this crude. So we have a cold region, and then we have a hot region in the middle, and then we're going to let the system evolve over time. Our intuition as to what's going to happen is that hot region is going to spread out, and then everything is going to come to equilibrium at the same temperature, right? So this is sort of schematically what we're looking at here. We have the distance from the center of the box at t equals 0. We have this dark color curve here where the velocities of the particles are very high towards the center and very low towards the boundary. And then as we evolve in time, we move from this dark purple to this light blue where the velocities are all roughly uniform. Okay, so this is like a very simple instance of relaxation to equilibrium. We can look at the same metric that we were using for the previous for the equilibrium discussion, except for now. So we're doing the same thing. We have the same number of particles, same energy. We just take a region in the center and we give the particles there 10 times the velocity, which is equivalent to just heating up the center of the box and then letting the sort of Newtonian dynamics take over. Again, gamma is the collision rate, which is related to the pressure. We heat up about 5% of the spheres. And what we see is, if you look at late times, these curves have the same behavior where it's constant with small fluctuations, but at early times, we get some sort of transient behavior, which is kind of interesting. And what we see is at low densities, this transient seems to last for a long time, but maybe has lower sort of amplitude, whereas at high densities, it irons out pretty quickly. Okay, so taking a look in a little bit more detail, this is what one of these high density boxes looks like in the inset here. So we have our spheres that are very closely packed together with one another. This is a crystalline configuration. You can see the crystal axes in the inset. And these red points here will come from starting the system in equilibrium and then just watching it evolve in time. And we see that the collision rate fluctuates around some average. The blue curve will be the sort of inhomogeneous case where we heat the center and the surrounding particles are cool, but overall the energy is the same, and then we evolve it in time. We see that the collision rate starts at some some significantly different value, bounces around a little bit, and then eventually they both end up fluctuating around the same value. So even if we drive the system out of equilibrium, it will come to find the same states statistically over time. Is this clear what I'm talking about here? Okay. So this is sort of like basic explorations in non-equilibrium physics. Now we have this causal graph. The causal graph is giving us the collision rate, but it's not really using the causal graph in a super deep way. A possibility which is motivated by the causal graph is we have all these particles, and what we do is we take the path associated with each one, we sort of pluck it out of the causal graph, and then we get the collision rates from that thing. So it's reasonable to divide the paths into two sets, one set being associated with the particles which we initially gave the enhanced velocity to, which we will call the hot particles, and the other set being associated with the rest of the particles, which were initially cold. But again, this is just, the particles just have velocity and position information. So the initially fast moving particles and the initially cold moving particles, and we can look at the collision rate for each of these two separately and then take their difference. So if this curve is positive here, it means the initially fast-moving particles are colliding more. If it's negative, it means the initially fast-moving particles are colliding less than the initially slow-moving or initially cold particles. And what we see when we calculate this as a function of time is this thing rings down to 0. So, excuse me, at long times, all the particles are equivalent to one another. And everything is basically doing the exact same thing, but we see that we have some transient initial behavior as the collisions propagate through the hard sphere sort of substance and things even out. So initially the hot particles are colliding way faster, and then they impart their collision to the cold surroundings. And interestingly, they end up the particles which were initially hotter end up colliding significantly less than the particles which were initially cold, and then they collide a bit more and then a bit less, and this rings down. And this is a signature of what can be thought of as sort of a compression wave through the system. So we have this hot sort of nucleus sitting at the center of the box. Those particles are moving super fast and they slam outwards into the cold material which is sitting around it, and they deposit most of their kinetic energy to that substance, and then they're moving very slowly, whereas the substance that they just slammed into is now moving much faster, and then that sort of compression wave reaches the boundary and everything ends up mixing together until all the particles are doing exactly the same thing. But there is some transition region which can be seen from this sort of back and forth between the two sets of particles. Is this clear? And to add one more piece of information, we have phi equals 0.62. So this is a very high density state, and phi equals 0.49. This is, excuse me, this is a slightly lower density state. So we see that there's a density dependence to the manner in which these compression waves propagate through the material. Okay. So what we can do is we can take a curve like this red curve or this blue curve for each density and associate a time scale to it. And that's what's depicted here. So again, we have the density on the horizontal axis. This is the time for that kind of inhomogeneity to relax on the vertical axis. And we see that at very low densities, it takes some amount of time for it to relax. At very high densities, it relaxes quickly. And just as a reminder of what we're doing, we're looking at these same collision rate curves, and we're sort of taking them apart to try to figure out precisely what's going on. Okay, so we've figured out that there's some time scale of relaxation associated with the system, and the reason why the fast ones relax faster is because there's more collisions. They're at higher pressure, so there's more collisions happening per unit time. And basically, the mechanism by which the inhomogeneity smooths out is simply collisions. The more collisions you have, the faster it will smooth out, and that's the origin of this relaxation behavior. Okay, I saw there was a question, but the hand went away. So if you still want to ask it, please feel free.
I do. So it's about those spikes around like 0.3 something, 0.5 something, and just a little for 0.6. Are these like, just some numerical errors, or there is something systematic happening there for
That
those
is
spikes in
that
the
is a
register?
good question. Yeah, that's a good question, and I'm not certain that I have an answer for you. In fact, I do not have an answer for you. It's still my suspicion is that okay, there could be a couple of things going on, but we did one experiment at each density. Okay, so it's perfectly possible. These systems are they have 4,000 particles in them, and we run them for a lot of time steps. So we get good statistics in some sense, but I wouldn't say that we have good ensemble statistics in the sense that we run these simulations many times and we see whether this behavior is precisely the same across ensembles, if that makes any sense. So as to whether this curve would look precisely the same if we were to restart the simulations and do another similar thing, but where the velocities are randomized in different directions at t=0. I'm almost certain that the curve would qualitatively look the same, and in fact, it would be pretty close, but there would be small deviations. As to what's happening in this transition region here and down here, you might recall going back to this guy here, that these are right where these non-monotonicities are occurring. So we might have a situation where we have like a crystal nucleus in a fluid sort of situation in this transition region, or the reverse, where we have mostly crystal, but there's still a little liquid pocket or something like this. And that could influence in detail the relaxation times here. And I think actually that will be the bigger source of uncertainty is the initial state that we're starting from, or the bigger source of sort of change of this curve. But the broad picture is certainly going to look like this.
Okay, thank you.
Not a very satisfying answer. I mean, one thing that I'm going to get to shortly is that it's very expensive to generate the initial conditions for these simulations. Evolving them in time is not so bad, but the initial conditions are super expensive, especially at high densities. So we just did it once, for better or for worse.
That probably would have been my next question about the complexity, but it just I ask it because it seems like most of the spikes are going up, but like if they are random, I would expect some spikes are going up, some spikes are going down, but like it seems like there is consistently going up at whenever there is like they go away from this down
That is
trend.
yeah.
So
No,
that's why
thank you for observing that. I'm going to write something down. That's a really good point. And it is interesting that the spikes go up, because if it was a solid sort of pocket of material or something, it would be associated with a higher collision rate, and we would expect the spike to go down. So that's intriguing. Xerxes, this is something for us to think about. Maybe we say something, maybe we don't when we write the paper, but that's a really good observation. Thank you. Do people have other questions? Okay, so we're using the causal graph in a way, and we're doing some non-equilibrium physics. And this is kind of interesting. We're learning something about the solid state in hard spheres and the fluid state as well. Okay, so that's one kind of perturbation. We heat up everything in the center, and then we let it run, and we see what happens. I'm just going to check the time. Xerxes, we have 17 minutes until the 2 hours is up. Is that right?
Yeah, if you need a little more, it's fine. But yeah.
No, that's fine. We'll see how we do. But it should come in pretty close. Okay, so we're now going to look at something else. I showed you this phase diagram at the beginning. What we've been looking at is we've been staying to the solid black curve here, right? So everything we've been doing, we prepare a system at equilibrium, and then we stick a hot poker into the center of it and then let it work itself out or something like that. We never landed our way onto this metastable branch here, but it's a reasonable kind of perturbation to ask, suppose we prepare the system in some metastable disordered state. So here we have a high density crystalline configuration depicted here, whereas what's taking place on this metastable branch, we have some sort of like supercooled liquid glassy kind of state. It's at the same density, but there's no spatial order. Okay. Now, one question would be, I prepare a system in a situation like this. How long does it take for this to work itself out and relax to a crystalline configuration, which is the true ground state of the system at the same density? Okay. So that's the other kind of perturbation that we're going to look at. There's a procedure for doing this, but basically, in order to get the crystal, okay, yeah, I'll speak very briefly about this. In order to prepare a high density crystalline state like this, we don't just choose a face-centered cubic crystal and put down particles along the I don't know, the lattice sites of the crystal, or however you want to say it. What we do is we actually generate this by a dynamical procedure where we put a bunch of point particles in the box, and then we slowly grow the radius of those particles over time. And as this thing evolves, you grow the particles until they're at their full size. The idea being once they reach their full size, the system will spontaneously form a crystal. Now, that's a well-established procedure. If you grow the sphere slow enough, in fact, you will spontaneously get a crystal. This is one such example. However, what you can do is you put a bunch of point particles in the box and then you blow up the sphere super quickly. And I guess you can roughly think about this as you put a bunch of beach balls in a box or in a big box or something. You just blow them all up super quickly. If you open that box, you're probably not going to get just like a perfectly crystalline arrangement of beach balls. They're going to be all squashed against one another. And that's basically what you do in this case to get a metastable liquid. You don't give the system time to crystallize. You squish it really, really quickly, or you blow up the spheres equivalently really, really quickly, and the disorder gets sort of frozen in, and you get some disordered amorphous state. And this is roughly what people mean when they're talking about like a glass, some spatially amorphous solid. Okay, is this clear what roughly how this is done? And I mentioned that it's super expensive to generate initial conditions. It's much more expensive to get crystals than it is to get these things, because you have to crystallize very slowly, like insanely slowly. You have to do like billions and billions of time steps of your simulation to get a crystal, because if you try to crystallize it too fast, it won't be able to find an ordered configuration. But this, you just make it go faster and it will find a disordered state always. So life is easier in that sense.
I have a question. So to get a crystalline state, does the kinetic energy have to dissipate of the system?
Good question. So as you are blowing up the spheres with time, there's kinetic energy associated with the moving surface of the sphere, which means that you have two particles colliding, but they're also inflating as they collide. So that collision actually does not conserve energy. It adds energy to the system, which means that if you run one of these for a very long time, the energy is just going to diverge. So yes, you're right. You add dissipation by simply freezing the system and decreasing the speed of all the particles and then keep going. You have to do this a bunch of times because otherwise the energy just goes crazy. The idea being the important detail of the initial condition from our perspective is the spatial arrangement of the particles, not the energy that it took to get there. Because we want to hold the energy constant for this in all of these studies so that variable is not affecting what we see.
And they're just colliding with each other. There's no electrostatic potential.
Yeah, there's no other potential. It's just the hardcore interaction.
And you said that they're getting bigger when they collide?
Yeah, that's right. I mean, so there's just some parameter that you introduce. You say at t equals 0, the particle has size 0. At t equals capital T, it has size 1. And then you just linearly grow them as a function of time. This is a procedure. It's a protocol. It's not like the canonical way of doing this. If you could easily find a high density configuration by some other means, that's also a valid way of doing this. This is just, it turns out this is one of the easiest ways, because depending on the rate at which you grow the particles, you either end up with a crystal or a glassy substance.
Yeah, an amorphous sort of solid.
Yeah, so and that's just a single parameter that you change. So that's why we chose to do it this way. And it's one of the standard procedures. There aren't that many. The other one, another example of how to do this would be you put a bunch of particles in a box, you give them some pairwise potential between them, which instead of being a hard sphere potential, it's 0 when they're not touching, and then it's just some rapidly growing smooth function when they are touching. And then you could use a continuous energy minimization algorithm, like a gradient descent kind of procedure, to try to move them off one another. But you have to get the energy all the way to zero if you do that, because you can't have any overlap between the particles. So we decided to not do it that way. That's another way that one could go. Okay, any other questions? Sure. Okay, so this is another kind of perturbation that we can do. And now we're just going to let it evolve in time. So we know that at the same density, you can make some glassy kind of state, but the ground state is a crystal. So presumably under time evolution, it will just find the crystal state. So let's see what happens. Again, we look at the collision rate as a function of time, and we see, okay, there's some transient behavior just like we were seeing before. But if you look in detail, this is the equilibrium equation of state. And then if you look at the same density, let's look at this highest density data point. We have a collision rate of something like 20 at equilibrium. And then if we look at the highest density state here, this collision rate is something like 80. So it looks like there's a problem here. Maybe there's some transient behavior, but the system is trapped in a metastable state. Even after 50 time steps, you'll recall that the relaxation time at most is 20 in the case that we were looking at before. We're nowhere close. Our collision rate is 4 times what it was before. So we can visualize this a little bit more concretely by putting the equilibrium collision rate and the rapidly compressed collision rate on the same plot. We get this thing where the rapidly compressed system looks like it's trying to settle down, but in fact, it's at a dramatically higher pressure than the equilibrium system. And it doesn't look like, I mean, in the inset here, what we can do is we can run the simulation for longer, 5 times as long, no, excuse me, 10 times as long, and see what happens. And after this initial transient, there's some power law kind of decay to the collision rate, but the power is 1 over t to the 0.067. So this state, if you want to be generous and extrapolate that curve and say, yeah, it'll eventually reach equilibrium, it'll take like 10 to the 9 time units, something like that. But really, it's basically arbitrarily long to reach back to the equilibrium state. So this is kind of interesting. What we see is we rapidly compress the spheres into some glassy state. Glassy, by the way, is basically defined by this characteristic where you just ask how long does it take to relax to equilibrium, and the answer is basically arbitrarily long. That's sort of a functional definition of what it means for something to be glassy. So we rapidly compress, we ask how long it takes to reach equilibrium, and we see that it basically has no hope. So this is an interesting, different kind of perturbation that we've done to the system. We saw that if we just have some temperature inhomogeneity, that goes away very, very quickly. But if we rapidly compress the system, we get some totally different kind of behavior, which I don't know, I would argue is moderately interesting. The same system can relax quickly in some circumstances and never relax in other circumstances. And this physical process that we're talking about is called structural relaxation, by the way. The relaxation of the spatial structure to its equilibrium configuration, as opposed to, let's say, its velocity distribution or something like this. Okay. Any questions on what's happening here? Why might be a separate question, but the details of the setup. Okay, so let's see, where are we going with this? Okay, right, so let's see if we can get a sense of what's taking place in this glassy phase that isn't taking place in the crystalline phase. So again, we're going to go back to the causal graph, but we're still going to take this perspective of looking at a single path at a time. So far, we've been using the collision rate, which can be extracted from one of these paths through the graph, and it's related directly to the pressure by some equation that we discussed. Another thing that we can do when looking at one of these paths, again, we can take a look at the green path, which we saw was associated with particle 3 based on that discussion that we had earlier. And we can just ask, who does particle 3 meet during its travels? So here, particle 3 collides with particle 2, then particle 4, then particle 2, then particle 4, then particle 2, then particle 4, right? So we have this Newton's cradle kind of configuration, and it makes sense. If you have the particles arranged in a line and you have periodic boundary conditions, it's only ever going to meet the particle to its left and its right along this line. So we can just sort of introduce another sort of metric and see what this gets us, is just how many unique particles does any particle meet over the course of its life. So for this graph, particle 3, the answer is 2, because it meets particle 2 and particle 4. And it turns out that all of them will have the same thing. They'll meet 2 unique particles over the course of their lifetime. If you have some particle I and it meets JKL over the course of its lifetime, maybe it meets them many times, then we'll just say it has 3 unique collision partners. Okay, so again, this comes from looking at the paths through the causal graph one at a time. This is the simple configuration where they're all arranged in a line, but it's reasonable to ask what happens if we look at the same kind of studies that we've been looking at, where we vary the density, keeping the energy the same. But now what we're going to do is we're going to look at the rapidly compressed system and compare it to the equilibrium system. Okay, so that's what's depicted on the right here. We run all these simulations for some same amount of time, 50 time units. The density increases from left to right, and we see that the equilibrium and the rapidly compressed glassy system behave basically the same until very high densities. So this here is in the solid regime. You're above the sort of freezing threshold. And then what you see is the equilibrium rate dies to some specified value, and the rapidly compressed system does something slightly different. Not super different, but it is slightly different. So I guess the coarse features to notice about this, it peaks at some moderate density. So what this means is if you have a moderately dense fluid, but where the system is not yet crystallized into a solid, those particles are moving around and they're encountering many other particles over the course of their simulation. By contrast, if you imagine a perfectly regular lattice, that particle is only going to ever meet the neighbors it exists in a cage, right? And it's only ever going to meet the neighbors that form that cage. It's not going to move through the substance and meet a bunch of other particles. So we see that at very low densities, their collisions are rare, so you don't meet that many particles. At moderate densities, there's a lot of mixing that takes place. And then at high densities, it starts to settle down. This horizontal dashed line here is the kissing number for spheres, for monodispersed spheres in 3D. So for those of you who are mathematically inclined, you probably already know what this is, but the idea is you put a sphere in space, let's say at the origin, what is the maximum number of other spheres that you can range around that sphere so that they're all touching? That's the kissing number. And what we see is at very high densities in equilibrium, this number of particles that any given particle is meeting is precisely the kissing number, which means that it's just arranged in some regular lattice, and all it's doing is rattling around in the cage formed by its neighbors. And you don't get any sort of redistribution. The blue curve, the rapidly compressed system, sits above this for a density interval. So what that means is that even though you have this amorphous collection of particles and they're all sort of tightly pinned against one another, the fact that the number of particles that they meet is greater than the kissing number means that the lattice is still rearranging. So you have this high pressure thing, they're all trapped together, but there's still some degree of movement taking place where it's not like the randomness is frozen in and everybody is just rattling around their neighbors. There's some degree of movement of the particles. And then there's some indication at the very, very end that you might be dipping below the kissing number, maybe. I mean, within error bars, you can't really say that, but you can imagine a situation where everybody's perfectly pinned, and then that number would actually be less than 12. But we see in this narrow interval, we have some degree of rearrangement of the spatial structure of the solid. That's sort of the key takeaway from this. Do people have any? Is that roughly clear what I'm saying there? We're almost done, I promise. You all have been very patient. Thank you for your patience. We have one more set of results here, and then I'll be done, but it's pretty quick. So we haven't talked about light cones. We've been using paths the entire time, but we should make use of the light cone. It's a very natural construction from this perspective of this causal graph. So again, the idea of the light cone being it starts from a single collision, and then all of the collisions which happen in the future of that collision involving those two particles get swallowed into the light cone. So you can think of this as like the propagating effect of all collisions downstream of any given collision is the light cone. So we want to take a look at, I think perhaps the most useful way to look at this is how this looks in space. So that's this result, and this is the last result. So I'm almost done. So everybody can hang on for a few more minutes and then I'll let you go. So what we have here is we have two different systems. On the right, we have a glassy system of the kind that we were discussing where you rapidly compress And then on the left, we have a crystalline configuration. What we do is we take a random collision that just happens in the center of the box, and then you let the simulation, you look at a light cone as it evolves for a certain amount of time into the future, and then you cut it off. So on the left here, we choose a collision, and then after t equals 1 in simulation time, a bunch of collisions take place, and then you cut the light cone at that point. Now the question is, what are all the collisions that have been affected by that collision that we started with? So what's pictured here is if a particle has been included in that light cone, we color it red. Otherwise, we don't color it in at all. So you really have like a full crystalline solid in here, but only a subset of the spheres have been colored in. On the right, we do exactly the same thing. We choose the collision in the center of the box. That's 2 particles. We cut the simulation off at a certain amount of time, cut the light cone off, excuse me, after a certain amount of time. And then we look at who is in the light cone after the certain amount of time. So same number of particles, same energy. It's just that this is a glassy system and this is a crystalline system. What we see is we have about 6,000 particles on the left, a little more than that on the right, but this one was run for 5 times less. This light cone was cut off after 0.15 as opposed to 1 in terms of duration of time. So this is interesting because roughly to 0th order, what we see is these light cones correspond to sort of spherically expanding fronts inside the gas, where you start with just a pair of particles that are highlighted. And as time goes on, you sort of add more to this little structure, and it grows roughly spherically. Obviously, there's texture to these things, but it's basically spherical. But in the glassy phase, this grows much, much quicker than in the crystalline phase. And this is kind of cool because if you think about this is how collisions propagate through a substance. If you think about sound as just being you compress the system and the compression propagates through the substance, as a function of space, let's say. What we can see from this is that we expect a glass of hard spheres to have a much higher speed of sound than a crystal of hard spheres. So you have a long system of hard spheres, you compress at one end, and then those collisions just propagate through the substance. For the crystal, it'll propagate at a certain rate, but for the glass, it'll propagate 5 times as fast or something like this. So it makes sense to think that a glass will have a much higher speed of sound than a crystal of hard spheres. Okay, so again, we have to sort of rush through that part a little bit, but the takeaway is that the light cone also gives us some indication of sort of how disturbances move through the system, how collisions move through the system. And the sort of what I hope I've been able to communicate during this talk is that the way that collisions move through the system it's the only sort of mechanism that the system has to relax to equilibrium. When we have the higher temperature thing, the higher temperature region in the center that then smooths out, all of that is just particle-particle collisions. And the same thing with the glass. If it wants to relax the structure, all it has is particle-particle collisions. So the light cone gives us sort of an indication of how that actually moves through the system and what the details of the relaxation process look like from any given collision as a starting point. Okay, I'm now officially over time, so I think that this is basically what there is to say. I'll do a very brief wrap up. The causal graph it complements existing information on the hard sphere system. So we run a time evolution, the particles move in space and their velocities change. We can construct this causal graph. It's not exactly clear at the outset what it offers because we extracted it from the dynamical evolution, but it offers a new perspective. So it's sort of complementary to existing sort of phase space information. We can look at individual paths through the causal graph, which give us things like the collision rate, which is related to the pressure. And it also gives us this sort of number of neighbors that the particle encounters during its evolution. The collision rate lets us look at equilibrium physics as well as non-equilibrium physics. And this number of neighbors gives us a little bit of insight into like, okay, I have this amorphous solid state and I have this crystalline solid state. What are the particles doing under time evolution in both of those circumstances? And then if we look at the light cone, we can look at, okay, what is the causal consequences of a given collision? We see they propagate through the system in a somewhat regular manner, but the details depend on the spatial arrangement of the particles. So we can use that to sort of compare and contrast the crystalline and glassy configurations. We see glasses very probably will have a higher speed of sound as a result of the collisions moving very quickly through the substance. Okay, so going forward, we're going to publish. Xerxes and I are writing the paper. This is very exciting. It's been a long time coming. Thank you all for listening. I realize I've been sort of taxing your patience. I've been speaking continuously for 2 hours, but that's what I have to say. So happy to take further questions and also happy to release you to the universe and to your lives. So thank you.
Thank you. Let's take questions.
So may I ask a question?
Go ahead.
I didn't see who spoke, so Pavel, I saw you spoke. Go ahead.
I think it was Pavel, yeah.
Okay,
Yeah,
good. Thank you very much. So you did not mention throughout your talk entropy. I would expect at this point somehow to also, because there's some physical notion of entropy, right, related to systems of equilibrium. There's some informatics notion of entropy. So have you looked? I'm not an expert in that, but have you looked at it from this point of view?
Yeah. So this is the entropy is something that people certainly do think about in the context of hard sphere systems. I mentioned a little bit. One of the most confusing points of the talk, entirely by fault, was the discussion of excluded volume. And the entropy is very closely related to the notion of excluded volume. But I will say, I can say something very briefly about the role of entropy for systems like this. There's some question of why is the crystalline branch of this equation of state here the actual ground state of the system, and why is the metastable branch an excited state as opposed to a ground state? And partly, obviously, the pressure is higher at the same density, but also sort of a flip side of that story, or another detail of that story, is that the crystalline state at high densities is a higher entropy state. This can be thought of as there are more ways of sort of arranging a crystal at high densities of hard spheres than there are of creating a disordered solid. If you just think about the number of microstates, the number of equivalent microscopic ways at the same pressure and volume, let's say, it's actually comparatively difficult to make a disordered packing because they're all pushing up against one another as it is to make a crystal. And that's reflected in there being more crystalline states than glassy states at the same density. So that's one aspect of the entropy discussion. The other thing is that entropy is not used so much for non-equilibrium physics kinds of things. And I think, people can extract whatever value from this discussion they thought. I think the most interesting physics that we've done in these studies are the non-equilibrium aspects of the studies. Because people have come along and they've done equilibrium with better statistics and more accurate algorithms, blah, blah, blah. But the advantage of doing this molecular dynamics approach is that you can drive the system out of equilibrium where more interesting things are likely to happen. So entropy does not carry over quite as well. There's a secondary discussion about the role of entropy in the physics of the glassy configurations up here. But we're moving out of my domain of expertise. In that case, they use equilibrium techniques to understand this sort of glass branch of the phase diagram, and the entropy figures prominently. But in some sense, we just didn't decide to focus on it, if that makes any sense. Good question. Okay, Mohammed.
So it's kind of related. So basically, the reason why you were able to do a very non-equilibrium physics very easily with the system is because you reduced the phase space or your configuration space from coordinates and momentum only to events as collisions, right?
Yes, you can think about it that way. Sure. I mean, there's all sorts of things. You're sort of confronted with the question of, okay, I just have positions and velocities as a function of time. What can I do? Now, we've decided to focus on the causal graph because it's related to Wolfram physics. But yeah, in some sense, you could just say just starting from the causal graph, which throws away phase space information, but keeps time and that kind of thing. What kinds of questions can I answer? So in that sense, yes. But it sounds like you had a follow-up question.
Yeah, my follow-up was basically, do you know how much like computation wise, how much like the complexity decreases when you consider only events or collisions rather than like the whole statistics of configurations, and the same with like computation time and storage, because it's still like definitely costly, because we're considering a three-dimensional system with a lot of events and a lot of particles, but at the same time it should be much better than the configuration space as a whole.
Yeah. Okay. So there are two aspects of this. There's the storage, which I'm glad you pointed out. As you say, there's the storage, and then there's the simulation itself. The thing which I tried to set this up, and maybe it was not super clear. The causal graph is something that is extracted after you've completely run the time-dependent phase space simulation, right? So we're totally evolving the positions and velocities of all the particles for all time of the simulation. Now you can ask about what you save from that. The causal graph, in some sense, is a very compressed way of storing information about the system, because you just store a list of the collisions, which are these things here. Sorry for the rapid scroll on screen there, everyone. But you just store a list of these triples. Now, in a time-dependent simulation at high density, you might have, I don't know, 100 million of these things. But 100 million ordered triples of numbers is not as bad as 100 million states of the system, each one of which is 3 numbers for position, 3 numbers for velocity, 4,000 particles. Now you're talking about like really large amounts of data. The flip side of that discussion being, you need to efficiently represent your graphs. If you have 100 million collisions, then you have a graph with 100 million nodes and 200 million edges. You need to think about an efficient way to represent that. But there's a straightforward resolution to that problem. You just have to think a little bit about how to do it. So you don't get any acceleration of your numerical simulation of the system. You do get a somewhat compact representation of the output of the system which you can use to do a bunch of physics. But yeah, there's no free lunch here. If that is that what you're interested in knowing?
Oh, no, yeah. Like you're basically saying the simulation time does not get affected, but the storage,
No.
which you actually use and care about, gets affected much. And I think like mostly
Correct.
the storage is like what really kills most of simulations. If you wanna keep like the state of like taking pictures of the system at like
Yeah, that's right.
like slices of time,
Yeah.
that would definitely kill your simulation. So yeah.
Yeah, and
Thank
we
you.
can, yeah, you the storage can blow up like crazy if you're not careful. Because I mean, a typical time step for this system will be like 10 to the minus 6 or 10 to the minus 7, and then you run it for a total time of 50. So you have 50 divided by 10 to the minus 7. That's the number of frames of your simulation. And if you imagine like the worst case storage, it gets huge. So you can always fill up your hard drive if you do something silly, but we're yeah, if you want
Yeah.
to just store this, it's very compact. Okay.
Okay.
Um
Thank you.
I'm gonna mess up your name. Jacopo?
Yeah,
Sorry.
the first one was really good.
Okay, all right.
Yeah, so I just had a quick question. What are the challenges in finding the sort of analytical equation of state for this problem? Is it like, I suppose the partition function, you can get it, right?
Well, okay, so that's exactly what we do. I don't know if you're somebody who's what a partition function is. So you've seen some
Yeah,
degree of
I have.
StatMech.
Yeah.
So the momentum space version of this partition function is no problem, right? Because your Hamiltonian just has the kinetic energy of all the particles. That turns into a bunch of Gaussian integrals, which you can do analytically. It's the other part of the Hamiltonian, which is this pairwise potential term, that causes the problem. So let's see. I didn't write it down anywhere here, but I do have this. Whoops. Okay. Well, we're playing the movie. But anyway, so this is the pair potential, and the Hamiltonian looks like a sum on I and J of this thing. And then you imagine e to the minus beta sum on I and J of this V xi xj. And that's fundamentally the problem. So you have to figure out how to compute that sum. And this is some, it's either infinity or 0. So the sum is either 0 or 1, but that doesn't mean that you can actually do it. So there's an approach. I don't know if you've ever heard of something called the cluster expansion, but the cluster expansion is sort of a systematic procedure for trying to calculate that partition function. But it involves it produces a bunch of diagrams, which are sort of analogous to Feynman diagrams. They represent integrals. These integrals get increasingly difficult as you sort of keep going. And in principle, you would have to sum all of them to get the actual equation of state. So what people do at low densities is they basically try to do this. There are sort of numerical ways of doing it, and there are analytical ways of writing out that expansion, trying to sum the diagrams and everything. But the thing about that is these go into calculating the so-called virial coefficients, which is you express the pressure as a power series in the density. That's all it is. And then you're trying to work out the coefficients of that power series. The problem with those virial series, it's very difficult to compute the coefficients. And even if you do, what they give you, again, my apologies for the scrolling. What they give you is they give you this low density branch, and then they give you the metastable liquid branch, but they don't predict any of the phase transitions. So all of this branch up here at high density and these things here, you have to do either numerics or do some mean field theory kind of construction. So it can be done, but you'll never get all the way there, if that makes any sense. Maybe that was too much information or not what you wanted, but
Thank you.
yeah, sure thing. Any other questions?
Just last one. I don't wanna, keep people beyond time a lot. You mentioned the cluster expansion, so I understand the cluster expansion in terms of discrete systems like lattice systems. But how do you do it in a system with continuous position or space like this?
Okay, there's a cheap answer and then there's the real answer. The cheap answer is I recommend David Tong's lecture notes on statistical physics. Those are excellent and you will teach you exactly how to do it. But the way that you actually do this is, let's see, you introduce something called the Meyer-F function, and you can express, which is like 1 plus e to the minus beta Vij, this Vij here. Whoops, this one. And then the partition function, so it's like e to the sum of I and j of beta times v, right? And that turns into a product of e to the minus beta Vij multiplied over I and j, and then you expand that whole thing out. And I think the cluster expansion is sort of like a systematic way of doing that expansion. It's been a long time since I've gone over it, but in some sense, it's just words that are attached to computing the partition function, the spatial part of the partition function, in terms of this pair potential. I'm not certain I have anything smarter to say, but you can turn it into an expansion where it starts at 1 because that's the ideal gas law, and then you sort of go from there. And as you add terms, the diagrams that you need to sum get more complicated.
It's like each diagram is going to consider a collision between more particles involved in events.
Yes,
Okay.
essentially. But by collision, really what we mean is we mean xi, xj, you fix I and j, and then you integrate over xi and xj, something like that.
Okay.
So it's not collision in the sense of time-dependent dynamics like the thing on the screen right now. It's collision in the sense of doing a phase space integral, but yes, yeah.
Okay. Thank you.
Yep. Anybody else? Pavel, I saw that. If you have something you want to say, you're welcome to.
No, I was just now searching through the internet if there is a notion of an entropy of a graph or something like this. If I could, I was just thinking I could compute somehow thermodynamical entropy and thermodynamic and entropy in some information sense and compare that in some way.
Yeah. The answer to your question is there's a lot of things that you can compute, and there certainly is a definition of entropy that you can associate with the graph. when we initially started this study, we were interested in seeing like this. We thought that maybe this causal graph, you know, in a fluid system or a solid system would have some crazy structure at the level of the connectivity. Like maybe as you solidify the system or something, the structure of the causal graph changes and you get like an isolated region, or you get like a big hole forming or something like this. Just the details of this construction are such that that does not happen. And in some sense, we sort of wanted that to happen because it would be like a really cool mathematical exercise and so on. And in that case, it might have been more interesting to associate some sort of like more traditional graph metric to this. But in fact, we found the most substantive physics that we could extract is in some sense these more like mundane path and light cone kinds of considerations. You're thinking along the right lines. At a certain point, though, we were forced to go with what worked and and what taught us things. We spent a lot of time in the early days of this project looking at various graph metrics, and it just turns out for this particular construction and this particular problem, they don't give a lot of interesting information. It's slightly disappointing, but it is what it is. Hey, last call. Thank you again, everybody, for listening. You were a really great audience, and you asked a lot of good questions. So best of
Thank
luck
you.
with the rest of your winter school. And I'll share these slides. My email is on there. So if you want to talk nuclear physics, or you want to talk glasses or hard spheres or anything like that, feel free to reach out to me. I would be happy to chat with anybody. So
What, how can I do that?
Thank you, Matt.
I'll share
Okay.
the slides on the Discord.
Well,
and
I have something to share with you. You're on the Discord?
I will log on to the Discord immediately after this. I've not logged on yet, but I'll throw an introduction in the welcome channel or whatever it is. There's usually some introductions channel, and then hopefully that
Yes.
will be enough to get a hold of me. Is that
Okay.
acceptable?
Yeah,
Of course, yes.
Okay.
Thank you, Matt. Let's thank the speaker, and thank you everyone for being here. We'll make the recording available soon, and let's continue the discussion in one of the Discord channels.
Thank you.
Thanks all.
Thank
Bye,
you, Matt.
everybody. See you later. Nice to
Bye.
meet you.